Ever wondered what really makes a modern factory hum? Or, how those massive power plants manage to stay so incredibly precise?
hmm
Today, we're cracking open the world of
What's truly foundational here is grasping the role of a PLC. They are essentially the unsung heroes of industrial control.
Right.
Robust, purpose-built computers that monitor real-world inputs, make lightning-fast logic decisions, and then precisely control outputs in critical processes.
Like what kind of processes?
Oh, picture them running everything from intricate cement manufacturing lines to massive power grids, packaging systems, even the sophisticated climate controls in modern buildings.
Wow, so everywhere.
Pretty much. And this isn't just some niche skill. The demand for PLC programming expertise is, well, it's exploding across sectors.
Huh.
Automotive, food and beverage, water treatment, oil and gas, material handling, just to name a few.
Okay.
Now, a common stumbling block, that many people anticipate is the cost.
Yeah, I was wondering about that. Sounds expensive.
Right, thinking you need pricey hardware and licensed software. But the guide makes a really crucial point here.
Okay.
Nearly every major vendor offers student editions, free learning versions, or fully featured trials, often 30 days.
30 days, okay.
And even after that, limited feature modes are usually more than enough for you to practice with.
So you can get started without a big investment.
Exactly. The real aha moment isn't just that the software is accessible, but that the conceptual barrier to entry, which people often think is huge, is actually lower than ever before.
That's a massive relief for anyone looking to jump in. So let's peel back another layer. What exactly is a PLC, like in the simplest terms?
Yeah, let's break it down.
The source makes it crystal clear. It's a specialized industrial computer designed to orchestrate machines and processes.
Right. Think of it like a highly reliable, super fast conductor for an industrial orchestra.
Okay, I like that analogy.
It constantly takes signals from input devices, like, say, a sensor detecting a box on a conveyor belt.
Uh-huh.
Then it processes that information based on a set of programmed rules, the logic you write.
Right.
And finally, it sends commands to output devices, maybe telling a motor to start or a valve to open.
Gotcha. And crucially, unlike my laptop, these things are built like tanks, right? Designed for harsh factory environments.
Absolutely. Dust, vibration, temperature swings, they handle it.
Okay. So, PLC programming.
To clarify, yeah, PLC programming
Mm.
is really about giving those industrial conductors their sheet music,
Okay.
creating the precise sets of instructions the PLC follows.
And how do you write those instructions? Is it like Python or something?
Well, the most common language, and the one you'll definitely start with, is ladder logic.
Ladder logic.
It's incredibly visual, actually, laid out almost exactly like electrical relay diagrams you might see on a blueprint.
Oh, okay. So that makes it easier for people with an electrical background.
Exactly. It makes
Yeah.
it remarkably intuitive for them. But while ladder logic is, the big one, the guide also highlights other important languages.
Right.
Function block diagram, which uses graphical blocks. Structured text, which is more text-based, kind of like C or Python, as you mentioned.
Ah, okay.
And sequential function chart, which is great for step-by-step processes.
So different tools for different jobs.
Pretty much. And if we connect this to the bigger picture, mastering these languages is what allows engineers like you to truly design, troubleshoot, and, optimize complex industrial automation systems.
Shaping how everything gets made, essentially.
Yeah, from your car to your drinking water.
That makes perfect sense. So, with that high-level understanding, what's the absolute first thing someone needs to wrap their head around to get started? Where do you begin?
Good question. The guide lays out the foundational steps.
Okay.
And step one is all about getting electrically smart.
Electrically smart. Okay. Why is that so critical?
Well, it emphasizes that a solid grounding in basic electrical engineering is non-negotiable because PLCs communicate directly with the electrical world, right?
Right. Inputs and outputs.
Exactly. So you'll need to understand how power works. AC for big motors, DC for sensitive electronics, and the basics of circuits.
Makes sense.
Beyond that, knowing about fundamental components like resistors and capacitors is key. And then the workhorses, the basics of AC and DC motors.
Okay.
But here's where it gets a bit more specialized. Transformers. And crucially, current transformers,
Yep.
CTs, and potential transformers, PTs.
What do they do?
They're clever little devices that let a PLC safely see and measure massive currents and voltages without, getting fried.
Oh, okay. Sorry.
And perhaps most importantly, for safety understanding earthing or grounding and protection with fuses and MCBs.
MCBs.
Miniature circuit breakers, basically industrial-grade circuit breakers. Safety first, always.
Absolutely. Okay, so electrical basics first.
Right, and that leads us to a really important follow-up question.
Oh.
Once you understand the electrical bedrock, how does the PLC actually sense what's happening in the physical world?
Good point. How does it know if that box is on the conveyor?
This brings us to step 2, basic instrumentation. PLCs don't operate in a vacuum. They depend on a whole ecosystem of field devices.
Field devices, like sensors and switches.
Exactly, sensors, switches, transmitters. Understanding these instruments is absolutely critical for effective PLC programming.
Okay, so what kind of instruments are we talking about?
Well, the source highlights key instrumentation topics for you to learn. Different types of switches, like the simple push buttons you press, or limit switches that detect mechanical positions.
Uh-huh.
Then there are relays, which are basically electrically controlled switches,
Right.
and, critically, transmitters. These are smart devices that convert physical parameters like a temperature or pressure reading into standard electrical signals,
Standard signals.
typically 4 to 20 milliamps or 0 to 10 volts DC. These aren't just on-off, they're robust, precise analog signals that allow for continuous measurement.
So not just, is it hot, but how hot is it?
Precisely. You'll also learn about analog to digital converters, or ADCs, how those continuous signals get translated into numbers a PLC can actually understand.
Makes sense.
And finally, specific sensor types. Things like RTDs and thermocouples for temperature, and proximity sensors, level sensors, flow sensors, pressure sensors.
Wow, okay. Lots of different ways to measure things.
Exactly. And this knowledge is what allows you to properly connect, configure, and program a PLC to truly interact with its environment.
Okay, so once you've got that foundational electrical and instrumentation knowledge down, the next big hurdle for a lot of people is often, how do I even get my hands on the actual tools? The PLC itself, the software.
Right, the practical side.
The guide tackles this directly in step 3. Selecting a PLC brand and software.
Yeah, and there are quite a few out there.
There's a whole universe of manufacturers: Siemens, Allen Bradley, Delta, Schneider, Honeywell, ABB, Panasonic, you name it.
Big names in the industry.
And each one has its own programming software. But here's the crucial pro tip the guide emphasizes again.
Which is?
Don't get hung up on buying expensive hardware right away. Choose brands that offer student editions, free trial versions, or even completely free software.
Like Delta's ISP Soft, for example.
Exactly. That's your gateway to practice without breaking the bank.
That's huge for learners.
Definitely. Some popular software you'll likely encounter include Siemens Step 7 or TIA Portal.
TIA Portal is their big integrated platform now.
Right. Allen Bradley has Connected Components Workbench, or CCW, Studio 5000, RS Logix 500.
Depends on the scale of the PLC, yeah.
And Schneider Electric's Unity Pro or EcoStruxure Control Expert. The absolute key here, the guide stresses, is to pick one.
Just one to start.
Yeah, dive deep into its environment and master it, the core programming concepts. They're remarkably transferable across brands once you understand the underlying principles.
That's really good advice. Focus first, then branch out if needed.
Exactly.
Building on that, once you've chosen your tools, we move to step 4, learning the basics of the PLC itself.
Okay, more than just the software then.
Oh yeah. It's vital to recognize that a PLC is more than just a box that runs code. It's an integrated system. Hardware, software, wiring, communication, it all works together.
Okay, so what does that involve understanding?
This step breaks down what you need to grasp. You'll differentiate between digital signals, the simple on-off 0-1 signals from something like a push button, versus analog signals, which are continuous, like those 010V or 420MA signals from a temperature sensor, allowing for precise measurement.
Got it. Digital versus analog.
Then you'll explore the PLC hardware itself. The CPU, which is its brain, the input-output or I/O modules where all those field devices connect.
Right, where the wires go.
Exactly. The power supply, specialized communication modules. Then there's the practical art of wiring and connections, how everything physically hooks up.
Seems important.
Very. And a hugely important piece, understanding communication protocols.
Protocols, like languages for machines.
That's a great way to put it. Things like Modbus, Profibus, Ethernet IP, these are essentially the languages different industrial machines use to talk to each other and to the PLC.
Okay.
And finally, an introduction to HSCADA basics.
Human-machine interface and supervisory control and data acquisition. Think of these as the factory's dashboard in a control center.
Ah, the screens the operators look at.
Exactly, where they monitor and interact with the entire system. This holistic understanding is fundamental for you to grasp how a PLC truly interacts with the real world and not just the code on your computer screen.
That makes perfect sense. It's like understanding the entire nervous system, not just the brain, right?
That's a perfect analogy.
And this is where it all comes together. Step 5, diving into the actual coding with ladder logic programming.
The fun part.
Yeah. As we said, it's the most common language, and its visual simplicity is its superpower, mimicking those electrical relay diagrams.
Very intuitive visually.
The guide wisely advises starting small and scaling up. You'll get to grips with core concepts like contacts and coils.
Your basic building blocks.
Yeah.
Like virtual switches and relays.
Exactly. Then there are timers, your TON, TOF, and RTO, used for everything from creating delays to controlling precise sequences.
Crucial for timing operations. Counters, like CTU and CTD, keep track of things, whether it's bottles on a line or cycles completed.
Counting stuff.
You'll also learn bit instructions for internal memory flags, comparison instructions for decision-making, like is this value greater than that?
Essential logic?
And basic math functions, add, subtract, multiply, divide.
Yep, you need those too.
Now, here's a pro tip from the guide. Mastering analog scaling is crucial for real-world applications.
Absolutely critical.
This is where you convert those raw sensor signals, say that 420 mMA, into meaningful engineering units.
Like 0-100 psi or 0-200 degrees Celsius, making the data human-readable and usable in the logic.
Exactly. So the guide suggests starting with bite-sized practice programs, maybe a simple motor start-stop.
Classic first program.
Blinking a lamp with a timer or counting objects, simple stuff to build confidence. And what's truly fantastic and a huge benefit for learners is that most PLC software offers a built-in simulation mode.
Yes, this is key.
This means you can test your code on a virtual PLC, seeing it run as if it were real, all without needing any physical hardware at first.
You can build and debug your entire logic right on your computer.
Amazing.
What's often surprising to new learners is that while ladder logic looks simple, mastering the sequencing and interlocking of these elements.
Interlocking.
Yeah, making sure things happen in the right order and safely. Like you don't want two motors fighting each other or a process starting before a safety gate is closed. That nuance is where the real skill lies.
I see, safety and sequence.
Exactly. And that's precisely why Step 6, practice with simulation in mini projects, is absolutely non-negotiable for your learning journey.
Right. Gotta practice.
The guide emphasizes that theory alone just won't cut it. Hands-on practice, facilitated by those simulation tools we mentioned, is the key to really solidifying your understanding.
Makes sense. You learn by doing.
These simulators are invaluable because they allow you to experiment, make mistakes, which you will do, and correct them in a totally risk-free virtual environment.
Without breaking anything real.
Exactly. So the guide provides concrete, actionable mini-project examples for you to try.
Like what?
Things like implementing a start-stop motor control with interlocking,
Right.
which is critical for safety, as we said.
Yeah.
Blinking a lamp, using a timer, a classic first program to understand timing. Building a simple conveyor belt system simulation with a counter. Setting up tank-level monitoring using analog inputs and that scaling we talked about. Creating a basic traffic light control sequence.
Oh, that's a good one. Logic and timing.
Yeah. Or even simulating a basic temperature control system, maybe using a virtual RTD input and applying analog scaling.
So these aren't just academic exercises.
Not at all. They directly build the problem-solving skills and confidence you'll need for real industrial projects and, frankly, for job interviews.
Right. Gives you something concrete to show.
Exactly. You get tangible experience even before you ever touch a physical hardware kit.
So if we kind of zoom out for a moment, what does this all mean for you, the listener?
Yeah, let's bring it together.
We've navigated the entire learning journey, haven't we?
Yeah.
From understanding what a PLC fundamentally is.
Right, the basics.
Through the crucial foundational electrical and instrumentation knowledge you'll need.
The bedrock stuff.
To selecting your cost-effective software, grasping the entire PLC ecosystem, the hardware, the communication.
The whole picture.
And finally, diving deep into mastering ladder logic and getting hands-on with simulations in these mini projects.
Step by step.
This guide and our deep dive into it truly lays out a structured, accessible, and, surprisingly cost-effective pathway to learning a critical skill set.
It really does.
The barrier to entry for this incredibly in-demand field is significantly lower than many might imagine, thanks to readily available software and a clear step-by-step learning path.
It's more achievable than people think.
Yeah.
Which brings me to a final thought.
Okay.
This raises an important question, I think, for you to consider.
Go.
In a world that's increasingly reliant on precise, automated systems, I mean, from the devices in your home to the infrastructure that powers our cities, how might your understanding of PLC programming not only unlock new career opportunities, but also empower you to critically analyze and perhaps even help shape the very future of how things are made and managed all around us?